lesson here, lesson 11, we are going to talk about strong and weak acids, strong and weak bases. So this is where you're going to get your list for strong acids, and they are right here. Actually, before we get to that, let's do this. Strong acids, you guys know this, or you should from lesson 1. Strong acids completely ionize in water. HCl reacts with water to give you H3O plus and Cl minus. That's our new definition of what an acid does. And what do you get out of that? When you react these together, you get 100% almost these ions. Is that a good conductor, poor conductor, or not conductor? What do you think? No. Good, poor, or no? Actually, very good, right? Look at all the free ions you have here. Look at all the plus minus stuff you have here. So, very good conductor. You would expect when you stick your conductivity meter in there to be 9, 10-ish, okay? Should be. What did you guys get for HCl yesterday? Somebody, anyone? Conductivity? 10. 10? Okay. Good conductor. Okay, we proved it to you yesterday. Here's a list of all the strong acids. There's 6 of them. You need to know these. Perchloric, hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric. So make sure you highlight those and write those down, or whatever the case, or circle them or whatever. A list of strong acids. Perchloric, okay? I'll even give you the formulas because I'm nice. You guys should know these though, correct? Comes from hydrogen perchlorate, hydroiodic. Hi. Pay attention. Hi. Hydrobromic. HBr, right? Hydrogen bromide, hydrogen iodide, hydrochloric, HCl, hydrogen chloride. Sulfuric comes from aqueous hydrogen sulfate. And the last one here is nitric, which of course comes from aqueous hydrogen nitrate. Those are formulas and names of the top 6, or the, sorry, not the top 6, so they are the top 6 on the data booklet, but the strong acids. So you need to memorize those. 6 strong acids. If it's not one of those, guess what? By default, it is weak. You could study the weak ones. I wouldn't, because there's a lot more of them. Okay? There's only 6 strong ones. What does strong acid mean? It's incredibly strong. You don't want to put your finger in it? True, but what does it mean? What does strong acids mean? We just did it. It's up there. Anyone? Yeah. They completely change into H plus ions or H3O plus ions and the negative ion. So anytime you put these acids into water, you get a lot of H plus ions, aka H3O plus, hydronium. Okay? If you take 5 milliliters of a strong acid and 5 milliliters of weak acid, and you put them into the same water, into the same amount of water, same volume of water, the strong acid will completely ionize, and you will have a lot of pH, a lot of H plus, a very low pH. Okay, it'll burn incredibly well your finger. The weak acid will still burn it, but not as much. Okay, because there's less hydrogen ions, because it doesn't completely break up. Okay. Here's an example of a weak acid. We've done this one before too. Look, double arrow. Still forms this and it still forms that, but look at how much actually ionizes. About 1%. So once again, if I don't think I have to tell you, out of 100, okay, you get 1 of those. Not many. Okay? Out of 100 up here, you get about 100-ish. Okay? Maybe 99 if you're lucky. Okay? The double arrow indicates that it's a weak acid. Okay? It's an equilibrium, it goes back and forth. Low conductivity here, true. Okay? low conductivity, very high conductivity. All right, moving on. Strong bases. What are the strong bases? The strong bases are all oxides and hydroxides of group 1 and group 2 except beryllium. Okay? All oxides and hydroxides of group 1 and group 2, not beryllium. Beryllium's the exception. I'll give you some examples. Sodium, group 1, oxide, is a strong base. Okay? Sodium hydroxide is a strong base. Okay? Group 1, potassium oxide, strong base. Potassium hydroxide, strong base. Why do the oxides form a strong base? I showed you the reaction on the previous lesson. They react with water, they give you hydroxide, hydroxide dissociates. Next, you might have barium oxide, barium hydroxide are strong bases. Okay, group 2 oxide hydroxide. Magnesium oxide, magnesium hydroxide, strong bases. And those are just some of the examples. Anything in group 1, group 2, not beryllium, with an oxide or a hydroxide is a strong base. Anything else is weak. Okay? You don't even have to memorize these ones. Well, you do, but there's not 6 specific ones. You just look over there. Any oxide, hydroxide, group 1, group 2, strong base, not beryllium. Anything else is weak. Here's an example of a weak base. We looked at that one earlier today. Once again, you'll notice that only about 1% actually turn into ions. Okay, NH4 plus and OH minus. So not very much. Okay, good. That is your list of 6 strong acids and your bases, strong bases. Make sure you know those. Okay. Real quick, we're not going to spend a lot of time on this. I will tell you right now, we're actually only going to deal with, in Chem 20, we only deal with monoprotic acids. So monoprotic, things like monoprotic. Only one hydrogen ion can be react to give you your hydronium. Okay? So when we think about formulas, we think about a 1-to-1 kind of ratio, reaction with water. Okay? So each H plus reacts with a water to give you H3O plus. Okay? That was what we call a monoprotic acid, and that's all we're going to focus on here. There is polyprotic acids, and you'll do these next year, so I will mention them to you because they are important. And in fact, you'll figure out how to calculate this exactly next year, because to calculate the pH of this is a little more in depth. Okay? H2SO4. If you think about H2SO4, it looks like this, right? H plus, and SO4 2 minus. That is a polyprotic acid. 2 hydrogen ions. Okay? The first reaction, we've done this already today, guys. The first reaction is always the same. 1 hydrogen ion attaches itself to the water to make hydronium ions. Yes? What's left over? H1 plus and SO4 2 minus. So this combined together here will give you that there. Okay? That would be step 1 again. Okay? Step 2, now this here, okay, reacts with more water, and don't forget there's a, once again, there's a 1 plus here and there's a 2 minus there. This will add itself onto water to give you that, and what do you have left over? The SO4 2 minus, which is that right there. Okay? That's how polyprotic acids work. All right? We're not going to worry about that, but I will tell you next year you will. Okay? We're going to worry about the monoprotic acids. Listen, even when this happens, sulfuric acid, is it strong or weak acid? Strong or weak? It's strong. We just gave you the list. You should know it by now. What's your problem, right? Sulfuric acid is a strong acid. Even though sulfuric acid is a strong acid, okay, look. Yes, it makes this and this, okay? Even though that's a strong acid, look how much this actually takes place. The answer is it's very minimal, okay? It doesn't happen a lot, and in some cases, it depends on the acid, that reaction there may or may not even occur, okay? It's not strong enough to. So even though that this one happens to be a strong one, we're done after that, and this is so minuscule in comparison to the first one that it really has, in the big scheme of things, doesn't really affect it a whole lot, okay? So just keep that in mind. But that's an example of a polyprotic acid. We have monoprotic and polyprotic bases. We're not going to spend much time on this. I will tell you once again, we are only going to worry about monoprotic bases, sodium hydroxide, barium hydroxide, potassium hydroxide, things like that, okay? The key here is to think, and I know some, well, maybe you are, maybe you're not, I don't know. Barium hydroxide has 2 hydroxides built into that formula, and I get that. But basically what we're saying is that barium hydroxide dissociates and gives you hydroxide. That's it, it's done. That it's not going to react again to give you another hydroxide somewhere down the road. That's why we call it monoprotic, okay? This is something called hydrazine. This is rocket fuel. Rocket fuel, okay? And actually, I probably should have double arrows here. But rocket fuel does react with water to give you hydroxide. This base here, even though it's weak, reacts with water again to give you another hydroxide. That's an example of a polyprotic base, okay? Where that base can react again to give you another base, a weaker one. When you have any kind of hydroxide, that's not an option. When you take sodium hydroxide and you put into water, you get hydroxide, you're done. When you take barium hydroxide, even though there's a 2 there, you put into water, you get hydroxide, you're done, okay? Those are monoprotic bases, and that's what we'll focus on in class here, okay? And finally, real quick here, the last thing, of course, is just a little bit what we talked about in the lab, okay? Now, just keep in mind, there is 2 ways to deal with acid and base spills. Dilute it, that's what I told you guys yesterday, right? Okay, no big surprise there. When you dilute it, you decrease the concentration, you make the pH weaker, whether it's a base or an acid, you make it weaker for those, and you reduce the harmful effects. You can neutralize it by adding a weak base or an acid to compensate for that. And you might say, well, that's silly, right? Well, in some cases you don't have an option, right? Now, in the lab, I would hope that if you spill acid on yourself, we don't start throwing base on you, because that's kind of, well, we could really do some major damage, eh? Especially if you went over with the base, right? And then we'd have to throw more acid back on you to counteract the base, and then we could throw more, it gets out of hand, right? It could turn out, it could be a long time before the burning goes away, right? Yeah. Anyway, no, we wouldn't do that, okay? When do you want to neutralize something with a base? Well, for example, in Alberta, northern Alberta, we had this little issue here. We had dumped a bunch of strong acid into a lake. The rail car overturned and dumped a bunch of acid into the lake. So that's a problem. I'm assuming some fishies went belly up, probably. Some plant life probably died. However, how are you going to fix it? Are you going to dilute the lake? No. I don't think that's possible, because it's already full of water. There's only so much water that's going to fit in there, okay? So we're not going to dilute it, so you probably got to react it with a weak base, okay? And you would want to do a weak base, so you want to make sure that you neutralize it at a slow, steady rate, and environmental concerns are taken care of, etc., etc. By the way, just so you guys know, one of the things that you will have to know this eventually, but we'll talk about this again in Unit 4. When you do go to neutralize it, an acid and a base always gives you what we call a salt. And you might say a salt. Yeah, it's another term for ionic compound. Always gives you an ionic compound in water. Okay? So if you hear someone talking about a salt, and it's not sodium chloride, doesn't have to be, just a salt in general, we're usually referring to some kind of ionic compound. Okay? And water. All right? And that's that there.